Today, inshallah, we are going to continue the magnetic circuit topics. Last class, we discussed the basics of magnetic circuits. We discussed the parameters like magnetic field intensity, like magnetic field density, like flux, and discussed the units of each term. Okay, and we used the Maxwell right-hand thumb to identify the direction of flux lines according to the corresponding currents. And also, we used Ampere's circuit law to define the relation between flux intensity and the corresponding current. We discussed also the pH curve and the relation between flux density and flux intensity. And we described the meaning of permeability, and we agreed together that we have the global permeability, which is equal to the relative permeability multiplied by the absolute permeability. And also we define the absolute permeability, which is the permeability of the free space. And also the relative permeability, we said that the non-ferromagnetic materials like aluminum, like copper, like free space, all of these, the relative permeability will be unity. However, for other ferromagnetic materials, we prefer to use the materials between 2000 and 6000 in the electrical machine course. And also we discussed the difference between the pH curve of each material, and we agreed together that the material of silicon sheet steel is preferred compared to the other two materials here, because at low value of H we can get higher B. Also at higher value of H we can get higher value in B for the same curve. So we prefer this because it's more efficient. And we define the relation of Ampere's law for the toroid core, made an analogy between electrical and magnetic circuit. And we stopped at this point, or we discussed the last point, which was the pH curve of the magnetic material. I would like just to refer to last thing here before moving to another discussion. We said we prefer to operate the machine or the magnetic core at the linear part and knee part, and not prefer to operate at saturation, because at saturation we may stick with the harmonics, and also there will not be corresponding increase in B or magnetic density if we increase the current of the supply. So it's not useful anymore to increase the current. I would like to refer to something important, that as you can see, the value of permeability itself is changing with the current or flux intensity, and therefore the reluctance as well will be changed. This is different to electrical circuit. In electrical circuit, the impedance or resistance is not changing with the increase of current magnitude. And if we have resistance in DC source or supplied by DC source, and we increase the value of current, the resistance itself will not be affected. It's independent. So resistance value is fixed. However, in magnetic cores, the reluctance itself is a function of magnetic field intensity or magnetic field density. So if we increase B and H, the reluctance itself will be changed, and also will be, and it will be increased. So this is the difference between electric and magnetic circuit. Let's assume an example for magnetic circuit in DC motor, for instance. we can see here that we have a cross-section of a machine which consists of one core called stator, which is the part which is not moving in the machine, and another cylinder here in the center, which is rotor, and this rotor is fixed on something called shaft, and this shaft is rotating inside the stator core. This is the electromagnetic device structure. As you can see, flux lines are moving from this pole to the other pole. Assume this pole based on the current direction. Assume this pole is N and the other pole is S. So flux lines are moving from N to S in that way. And you can see the flux lines are moving from the stator core to the air gap between the stator and rotor, and after that to the rotor core, and returns again to an air gap, and after that to the stator. So in machines, we have to make air gap in order to rotate the second core. Otherwise, the core will not move. So the air gap is very important. However, this air gap will consume a lot of MMF. So it's better to reduce the length of this air gap. Okay? And in machines, practically, it's several millimeters between stators and rotor cores. So this is the shape of the magnetic circuit of DC motor. We can see here that in electric machine, the rotor is physically isolated from the stator by means of air gap, as we discussed, and a cross-sectional view is shown here. Practically, the same flux is present in the poles made by magnetic cores and the air gap. We discussed that the flux is moving from core to air gap and then to rotor, and so continue and return back to the stator core in order to move and return to the same pole again. If the flux density is high, the core portion of the magnetic circuit may exhibit a saturation effect. This is very important. As we described in pH curve, if we increase the current too much and the H will be increased, we may reach to saturation region. About saturation means the core cannot increase the flux density anymore if you increase the flux intensity. However, in air gap, if you increase the flux intensity, the flux density will not be saturated. It will increase all of time. This is because in free space or air gap, the permeability or relative permeability is unity. So the relation between B and H is linear relation. Okay. A magnetic circuit having two or more media, such as here, core and air, is known as composite structure. This composite structure, we need to make equivalent circuit for it in order to analyze the performance of the magnetic circuit. Okay, let's start in how to represent this or convert it to a circuit in order to solve problems. However, we can start with simple structure of core instead of this complex dimensions. So let's assume here structure. Simply, it's one core like that. It's called the C-shape. This C-shaped core has, for instance, a circular or a square cross section, whatever, with a cross section area A, which is called A core, and an average length of LC. So this length is LC, and this core is supplied from a source of magnetic, which is Ni through this coil, and I is the electric current, and N is the number of turns of the coil. So when the flux is moving now, it will move in the core itself, and after that it will cross this small length air gap, which is LG, in order to continue moving on the core. Right. What will be the direction of our flux here? How we can determine the direction of the flux in the core يا شباب؟
By using right hand rule.
تمام. طيب
It
خلينا
should be clockwise, doctor.
سوري. اتفضل يا عبد الله. عبد الله بسام. او عبد الاله، سوري عبد الاله.
ايه هلا دكتور.
اتفضل.
By using right hand rule.
طيب يعني can you discuss to us how you can do that here?
نستخدم الابهام باتجاه الكرنت، واليد بتكون اتجاه باقي اليد او راحة اليد بتكون اتجاه
So again in English please. So the current is going to move with the thumb finger in this direction, okay? And the flux now we have in our side and behind the wire. If we use right hand rule, so
out of the page.
Out of the page. Come to us, you mean? But I mean, is it going to move in the core to the top or to upper or lower direction?
To the bottom.
Lower.
Upper.
Yes.
Upper.
So we assume here, because of this current direction, the flux direction will be in this way. So in this direction. Line is very bad. So it's going to move in this direction, is it right?
Yes.
Right. So the flux is going to move here in that direction, and when it reaches to the air gap, what will happen? Actually, in air gap, if the length of the air gap LG is small enough, and the area of cross-section of the core is large enough, all of the flux lines are going to move through the air gap, and there will not be any fringing or any missed or leakage flux. All of the flux lines will move through the air gap. And in that case, we can assume that the area of the air gap is the same as the cross-sectional area of the core. And this will be the case in all of our models or all of our problems. Okay, Shabab? So we will assume all of time that the cross-sectional area of the air gap is the same as the cross-sectional area of core. So if we would like to convert this to simple circuit like electric circuit, so we can say we have a source here of Ni. This Ni can be represented by a source here. And we have a flux moving here in this core, so this is the flux. And according to the material or the media we have here, we have two different medias. We have the core itself, which has a reluctance, so we have reluctance for core. And we have free space, so we have another reluctance to air gap. What is the value of each reluctance? Simply, reluctance equal L divide mu area. So L of the core, which will be given in the example, like LC here, and the cross-sectional area also will be given as A core here, and the mu of the core itself, which is mu naught multiplied by mu r. So this is the permeability of the core. So this is the reluctance of core. But what about the air gap reluctance? Similarly, L gap divided by A gap, which we assume that it will be equal to the A area, cross-section area of core, multiplied by the permeability of free space, which is the absolute permeability. Right. So we can say finally that we have B gap equal to B core, because B equal to flux lines divide area, and the area here are same for gap and core. So B gap equal B core equal to flux divided by area. So this is for this simple core. Let's make a solved example.
Doctor, sorry.
تفضل.
Why there is no fringing in the core?
There is no fringing in the core because we assume all of time that we have small length air gap. And
I am not talking about the air, the core itself. You said the core itself, the flux is
impossible to have leakage flux during moving in the core itself. Because we agreed from the last class that flux lines are preferred to move in cores instead of air because of the large reluctance of the air gap. Assume if you have two different impedances in parallel, one small impedance and one large impedance.
Okay.
Which impedance the current will prefer to move, in the large or in the small impedance?
In the small to balance the voltage.
Small impedance will find more current.
Yes, doctor, but in the impedance case, the current will flow to the small impedance to balance the voltage. In this case, the flux
the same. The flux also will prefer to move in the small reluctance. If you have two parallel paths for magnetic lines, it will select the smallest reluctance one.
Okay, but I mean, but why in the current case it goes to the small impedance to balance the voltage, but in this case to balance what?
يعني to balance voltage?
Because of KVL, the current on the
just describing the physical property. KVL or Kirchhoff voltage law just describing the physical property. Okay, the same is also here. Flux lines, we have core and we have free space. Which is better? Which has high or low reluctance?
Low is the core.
Exactly. For that, the flux lines will prefer to move in the core, not in the air.
But why? I still
because of the lower reluctance.
Okay.
This is the physical reason. Okay. If you would like to say, like in electricity, if we apply Kirchhoff voltage law, you will apply here also Kirchhoff voltage law. Okay, but Kirchhoff voltage law just describing the property, describing the nature of electrical circuit, and the same also for magnetic circuit because we are going to use it here also. But the physical meaning is what we are describing now. The current will prefer to move in the lower impedance. Okay. And similarly, flux will prefer to not move, because moving in core is not the right expression for magnetics, but the right expression is build up flux. The flux will be built up in the core, okay, not in the air gap. Is it clear now?
Yes, clear.
Okay. Here is an example. The figure below represents the magnetic circuit of a primitive relay. What is a relay, Shabab? What do you know about relays? Did you listen to this word before, or also the word contactor? Contactor or relay?
Yes, doctor.
What is the meaning of contactor or relation?
It's like electrical switch.
Yes.
Using the magnetic inside, it will switch whenever the current is passes.
Exactly. This is exactly the definition or the meaning of relay or contactor. You have electrical circuit and you need to make short circuit between contacts or terminals, and you can use magnetic core or magnetic circuit in order to do that. يعني what is the benefit of using that? Why we do not use just manual switch like the switch of light in our homes? يا شباب, why we use relay or contactor instead of the switches? يعني if only the function we need to on and off.
Is it so we can control it using electricity?
Exactly, it's for the matter of control and also for the matter of protection. So relays and contactors are mainly used in protection and control. However, the manual switch, you cannot use it in control or protection. And if the electricity is, if the current moving in the circuit of the switch is higher than the rating of the manual switch itself, the manual switch will not be interrupted. It will be damaged. However, for the electromechanical devices or electromechanical switches, we call it electromechanical because it's include a part of electromagnetic device, okay, like relay, like contactor, like these circuits. It can disconnect automatically based on a certain value of current. Okay, so this is the basic idea or principle of protection using electromechanical switches. تمام يا شباب? So this is one of the application of magnetic circuit. Here, the figure below show a relay. The coil has 500 turns, and the mean core path, which is the average length, equal to 360 millimeters. When the air gap lengths are 1.5 millimeters each, as you can see, we have two air gaps. Each one is 1.5 millimeters. A flux density of 0.8 Tesla is required to actuate the relay. So, in order to actuate the relay, we need an amount of 0.8 Tesla. Right. And here it is defined that the core is cast steel. So the material is cast steel, the magnetic material of the core. Find number A, find the current in coil. So how we can get the current, شباب? Now we have one relation which is going to be used in most of our problems. This relation is MMF, which is NI, equal to مين يقول يا شباب؟ NI equals what?
HL.
Exactly, HL plus, equals also phi, which is a flux, multiplied by reluctance. When we, which relation we can apply here according to the available data? You have the length, length of air gap and length of core are given. So L is given here. However, H is not given. Reluctance and flux are not given. Number of turns is given and current is required. So we need to calculate H. What's given?
Doctor, we can replace H by B over mu.
جميل. طيب, what is the value of mu or permeability? How we can obtain the permeability?
We need to find the core, the cast steel permeability.
Right, very good. So we can calculate or obtain H from the cast steel graph, or we call it as magnetization curve of this core. So we need the BH curve of cast steel. It's given already in this example, and we described it in the last class for the free materials. So we have the cast steel chart, and we can obtain H according to the value of 0.8 Tesla. Now this is for the core. What about the air gap? Because now we have two different H and L. Is it right? Because we have air gap and the core. So we can write the relation now, MMF equal, or NI equal H gap, L gap plus H core, L core. We can obtain H core from the cast steel BH curve according to the 0.8 Tesla. However, what about H gap? How we can calculate it? شباب, someone else can answer, please. Who can answer يا شباب؟ Abbas?
Yes, Doctor.
Can you answer, please? Again, the question is, now we could obtain the value of H core using the H curve. How we can obtain HG? Someone else can reply, شباب? Ahmed Saeed?
Yes.
Abu Hamid? How we can obtain HG?
I'm not sure.
Anybody know, شباب, how we can obtain HG?
Doctor, we put the flux density B over M0 or M naught.
Exactly. This is all. We don't need any chart for free space or air gap. This is right. الناس تصحى شوية معانا يا جماعة. طيب. So simply we can calculate or obtain H core from the chart of BH, and HG can be calculated directly as B divided mu of the air gap, which is the absolute permeability. So simply we can substitute in this equation and obtain the value of current. So here, as you can see, for 0.8 Tesla, we can use the chart for cast steel and get the corresponding value of H. The value of H is 510 ampere turn per meter. So we can now calculate the MMF due to core, which is HCLC. So this is the value of MMF of the core, which is here 184 ampere turn. Similarly, we can do the same for air gap, but after getting the value of H, which is B divided mu. But take care, we have here two air gaps. So you have to multiply L by 2. So we can see here the value of ampere turn is very high compared to the value needed for the core. Yani even for small air gap, which was here 3 millimeters only for the two air gaps together, the amount of the MMF needed is almost more than 10 times. Is it right? More than 10 times of the MMF needed for the core of length 360 millimeters. 3 millimeters air gap needs 10 times MMF compared to 360 millimeters core. So air gap consumes a lot of MMF. Right. We need to calculate the current, so we can calculate the total MMF and divide by N, which is 500 here, to get the required current. So this means we need 4.19 ampere to operate the relay to achieve a distance of air gap of 1.5 millimeters. Okay, شباب. So this is the start of the current needed at that distance. يعني, which means if the distance is 1.5 millimeter, 4.19 ampere are needed. So if the distance decreased, the amount of current needed will be decreased. You got it? So based on the area, the length of the air gap, we will consume current. Now, if the air gap reached to 0, we expect to have very low current. So this is the operation of relay. When the relay starts connecting, it will consume high current in the starting up till reaching to the desired gap, or desired air gap, or make air gap equal 0 length. At this case, the required current will be very small. We will see this in the other two parts of the problem, or in part C. Part B first, compute the values of permeability and relative permeability of the core. طبعا simply we have the value of B and H for the core. You can just divide B divide H. You can get the permeability of the core. Your mic. So we can simply calculate the permeability of core by dividing the value of
انا ما اعرفش اي حاجه، انا جاي بس اعمل شويه فلوس واروح لعيالي. دقيقه بتاع داعم هادي ما بيجرد مالي دعوه. انا ما اعرفش اي حاجه، انا جاي بس اعمل شويه فلوس واروح لعيالي. دقيقه بتاع داعم هادي ما بيجرد جاي بس اشتغل اسوي شويه فلوس.
معز. Okay. So we can calculate the permeability of the core just by dividing B core divide H, which here is 1.57 multiplied to 10 to power minus 3. So this is the permeability of the core. So what is the relative permeability? Just we can divide by the absolute permeability, which is 4 pi multiplied to 10 to power minus 7. We can find that the relative permeability here for the core is 1250. Okay, تمام يا شباب. So this is the relative permeability of the core. In part C, it's required if the air gap is 0. If the air gap is 0, find the current in the coil for the same flux density. Yani, if we have the same flux density moving, or the same flux density achieved on the core at 0 air gap length, which here is 0.8 Tesla, calculate the required current, which means the two parts of our magnetic circuit is completely attracted together. So what will be the required current? We expect to have lower current. So simply, now this part of equation is removed. So Ni will equal to H core multiplied by L core. So simply, you can obtain the current, which is I equal to the MMF for core, which is 184, divided by 500. So only 0.36 amperes are required at the completely contacted cores. تمام يا شباب؟ Any question? The next example, consider the magnetic system of the previous example. If the coil current is 4 amps, when each air gap length is 1 millimeter, find the flux density in the air gap. يعني the same, but he now start يعني asking for another parameter. However, يعني we need special way to solve this part, I believe, because B is not given. Simply the same relation what we have يا شباب. We have Ni equal to HGLG multiplied by HCLC, and we agreed together Hg can be calculated as Bg divided mu multiplied by Lg. In previous example, B was given, and we could use it in these two terms in order to bring the value or calculate the value of current. Now the current is given, however, Bg is not defined, or B is not defined, and H as well is not defined. And we have a problem now. We have two variables on one equation. So how we can solve this problem? Simply, when we apply here the available data, when we substitute with the available data, we'll find that B of gap or core as well equal to minus mu naught LC divided LG multiplied by HC plus Ni mu naught divided LG. Just simply يعني get B on the left hand side and move Ni to the other side. So this is now the relation of B. This relation is nothing but a straight line equation, function of H of the core. So if we represent this straight line equation and plot it on the top of the BH curve of our core, we can get the intersection point, which will represent the value of gap flux density, تمام؟ or general يعني in the flux density value. تمام يا شباب؟ طيب يعني if we substitute now the slope of the equation, which is this part, we can substitute, we can find this slope, and the other part here, which represented by C, we can calculate C as well and start plotting the line. So we calculated C and M and plot this line based on the straight line equation. We could find that we intersect the characteristic of cast steel at a certain point. So this certain point is the operating point of our core. So simply we can get this value, and this will be the value of the magnetic flux density. تمام يا شباب؟ Is it clear? جميل. So we could obtain here a value of 1.08 Tesla, which is required to draw 4 ampere from the supply and achieve distance of 1 millimeter air gap. If you would like to calculate the exact value of HC now, you can substitute in the equation Ni divided LC and get the value of HC, okay, which is the flux intensity of the core, or you can get it also from the equation. تمام؟ Here is another example, but I believe this example will take more time. We can discuss this example inshallah in the next class. And now we can open the discussion for any question, شباب. يا شباب, any question?